Welcome to the video. This is going to be the first video on chapter 23, Gauss' law. Before we get started, if you can take a look at the bottom of the left-hand side, you can see that there's an equation where the right-hand side has a dot product. A dot product is just a different name for the scatter product. If you have not reviewed the scatter product, please do that first. The first topic that we are going to look at is electric flux, and you will scroll down to the next page to see the definition of which. Let's first look at part A of this diagram, where you can see the vector E representing an electric field located at the center of a surface element shown in green. The area of the surface element is delta A, which is meant to be a vector. The magnitude of that vector is just the area of the surface element. The direction of that vector is perpendicular to that surface element. Therefore, in part A, the direction of the surface element delta A will be pointing in the x direction. Still looking at part A, we now have two vectors. The first vector is the electric field E. The second vector is delta A, and the electric flux is the dot product between these two vectors. So, if we scroll down, then we can see that the electric flux is given in terms of the scatter product between the two vectors, E and delta A. Now, what we have just looked at is a small piece of the whole thing, and therefore, in order to get the complete flux, we have to do a summation over the complete surface area, as shown in equation 23.1.1. And if we take the limit, then the electric flux will be defined as the integral of the dot product between E and dA. Let's come back to take a closer look at these three diagrams, and we will start from part A. Part A is our assignment. What we're supposed to do is to find out the electric flux for the situation given in the diagram. Let us recall the tools that are available to us. From chapter 3, we will recall the two definitions of the inner product. And we're also going to need the definition of the electric flux. In part B, we are shown that the electric field E has two components, and therefore the vector E can be written in a component form. The purpose of part C is to show that the area element has a magnitude of delta A in the direction that is pointing along the x direction, and therefore delta A can also be written in a component form. We now can apply the definition and obtain an expression for the electric flux. Now if you go back to look at how the vector E is drawn, that E looks like it is in the first quadrant. And you will recall that for a vector in the first quadrant, the horizontal component is the vector multiplied by cosine of that angle theta. And we will obtain a result that matches the first definition of the dot product. Let's also scroll down to look at this diagram on the left-hand side. What this diagram is trying to tell us is that no matter how complicated the surface is, at any location, in any surface element, there are always two vectors that you have to look at. In situation number 1, we have an electric field that is pointing due east, and we have a surface element that is pointing due northwest. In the second situation, the electric field is still pointing to the right, but the surface element is pointing downwards. And in part 3, the electric field is still pointing due east, but we have a surface element that is pointing due northeast. In each case, so long as we know the components of the two vectors, then we can calculate the electric flux. All these electric fluxes are meant to be summed together. The final form will have the look of an integral, as shown in equation 23.1.2. Let's stop for a moment and look at the terminologies that we're supposed to know. We've been talking about a surface, and this surface has a name known as the Gaussian surface. Sometimes the surface will be a closed surface. In this case, the surface will divide the space into two parts that are separate from each other. Take a basketball as an example. The surface of the ball will be a closed surface. There's the inside of the ball and there's the outside of the ball, and the two parts are separate from each other. There's also the open surface. If we cut a basketball in half, then the half surface of the ball will be an open surface, because in this case, the quote-unquote inside will be connected to the outside. If we further scroll down, then we can see that in equation 23.1.4, there's a notation that looks a little different, and that is this integral sign has a circle in it. Now if you look at the paragraph just below it, then you can see that this means this integral is meant to be calculated over a closed surface. So if you see a little circle in that integral sign, then you have to know that the corresponding surface will have to be a closed surface. And that completes our introduction to the definition of the electric flux.